Okay. I'm from University Carlos III of Madrid. I'm finishing one research visit here. And thank you very much for giving me the opportunity to present my work, one of the works that I've been doing here. Now we move on cybersecurity. And I'm going to talk about vulnerability detection under poisoning attacks, in this case, using image processing. Well, let's start just doing a motivation why I'm working in this topic. First of all, because of everybody knows the significant use of artificial intelligence for everything. Probably in your topics also, artificial intelligence is applied. So this is why we have to focus on that, especially since ChatGPT and all these things, we have to work with it. The point is that, well, in general, an artificial machine learning algorithm work in this way. You just collect data, you just process in depending on the way, and apply an artificial intelligence algorithms, train, test, and well, you just go to deployment production. Okay, but what does it happens is data from the beginning is in some way poisoned, because we are using a lot of artificial intelligence algorithms without wondering what's happening if at the very beginning we are using data which is not ground truth. Especially, I always use public data. I assume the same as you, and we have to ensure that this data is trusted. Otherwise, we will have problems. Now, if we move on to the topic of vulnerability detection, why working in this? Well, in security operation centers, probably in films, you have seen that, in which there are a lot of people just looking at the screens, waiting for attacks and malware and so on to appear. They need to identify if a piece of software, a piece of code, has a particular type of vulnerability. Is malicious or non-malicious, let's say, just to make it simple, okay? So this is why working in this area is extremely important, because you know that currently there are a lot of software and some of them has security problems, and we have to discover as fast as possible. And this is why vulnerability detection is important. In particular, what is a vulnerability? It's just a flaw or a weakness in the code, a security problem in the code, which may lead to exploit or to an attack. This is just a snippet of code. And here you can see, the vulnerabilities, all of them are identified by an ID, but this is not important. And in this case, it's used after free. Why? Because in this case, you have a variable PTR, and you make free, and then you use it. Okay, it's just an example of a vulnerability. Why? Because of this, different attacks can be carried out. So the point is to distinguish which type of vulnerabilities are within the code, trying to prevent attacks afterwards. So given the amount of code and the amount of vulnerabilities, it is important to work in this topic. There are many works related to detecting vulnerabilities. Now I'm gonna show you the work that I have carried out with plugin, also here. And this is the proposal. This is called IVul. And the idea is, we have code, we convert the code to images, just to make it simple, okay? We have code, we convert the code to images, and then we apply a neural networks, a convolutional neural networks, but just to make it simple, trying to distinguish which kind of vulnerability it is. Just is a CWE 173 or whatever, okay? So that's the general idea. What we have done apart from this is, first of all, this is the baseline. I mean, we have different data sets. I will explain you later, okay? That we have carried out this, just convert the code to images and apply the neural networks and see if it works or not. Okay, that's fine. But what we have also studied is, what does it happens if that codes from the very beginning at the training step are poisoned in some way? So we have applied the same technique, IVul, the same mechanisms, but analyzing what happens when the code is poisoned. I'm going to explain you a little bit more about it. what are the poisoning attacks that we have to carry out? The idea is to modify the code just just very briefly, okay? Just small modifications in the code, just for an adversary. An attacker could, for instance, function renaming. It's just to include lowercase, okay? Just in this way, okay? Just including something at the beginning and at the end of the function, okay? In this case, just a lower bar, okay? Then that co-insertion is just to include a snippet of code, very small piece of code, which is useless in some part of the code. And the last one is a space insertion. This is just to include double spaces instead of one space, just two spaces. You may say, this is, I mean, what are you going to get with that? You get quite more. I mean, you can confuse the machine learning algorithms and just doing that. And this is quite important because from the researcher point of view, or even those who are working in operation centers, in security operation centers, you can see this code. You can see this code and say, it's fine, nothing malicious. Yeah, but maybe because of that, the artificial intelligence algorithms could be misled. And maybe a vulnerability is not detected because of that. And so this is what we have studied. What are the main goals of this work? First of all, attack resiliency. It means that we want to develop a system as resilient as possible to all these kind of attacks. Obviously, we want to maximize security. It means that I want to detect as many vulnerabilities as possible. And we want to also maximize usability, meaning that we need to reduce the amount of fake alerts, because a lot of false positive or negatives maybe confuse the system as well. So what about experiments? We have used, one of the data sets that we have used is the SART. Maybe some of you know. This is just a data set of vulnerabilities collected from the NIST. In this case, we have used two languages, C# and PHP. We have also tested with C++, but it doesn't work. I will explain you at the end. So these are the couple of data sets that we have used to analyze all the attacks. And what are the threat models? Two of them. On the one hand, the first threat model is that the attacker wants to generate fake alerts. That's good. Well, that's good for the attacker, because if a lot of alerts are fake, then the ones sitting in the operation center say, this shouldn't be a vulnerability because I've received a lot and any of them is true. Okay. And the second one is when you receive a code which is vulnerable and the attacker wants to say it's not vulnerable. Okay, just to confuse the system to say a code which is vulnerable is not. Okay, that's the second threat model. Okay, with this in mind, we have used the most relevant metrics in our case, okay, which are accuracy, as you already know, false positive rates, false negative rates. In this case, false positive is directly related to vulnerabilities which are not detected, okay, samples which are undetected, and false negative rate is just directly related to fake alerts. Then, in the first threat models, we have analyzed the difference between the baseline. Baseline is when the original data set has not been poisoned, okay, just testing if IVul works or not, just the general system works or not. So we make the difference between what has happened after the attack and before the attack, just to analyze if the system works or not, what it is, the difference. And in the second threat model, which focuses on trying to get samples as no vulnerable when they are vulnerable, okay, we have computed the true positive rate, which is just directly related to vulnerabilities which are undetected, okay? They are computed according to this equation, just to compute it over the total. I mean, meaning that if you have 70% of true positive rate, this could be equal to 100% of true positive OT, okay? It's the same idea. So what are the results? Just to give you an idea, here I'm not going to explain you all the results because it's quite boring. If you want, you can read the paper. It's already, hopefully it will be published soon, but it's in my university repository if you want to read it. So baseline results, if you take a look for all the different vulnerabilities, okay, here there are identifiers. We have identified that the accuracy of the system, IVul, is extremely high in most cases. If you compare with the state of art about the vulnerability detection, this is quite comparable or even better. And what is the benefit of this system is that you don't need to preprocess the code. You just take the code, make a picture, and that's it, put in the network. And this is a quite big advantage. And because in other works, maybe you have to compute features or you have to create tokens or whatever, but this is even easier, okay? So that's the baseline. The model, the data sets are not poison, okay? That's the baseline. Now, just to show you an example with C#. In the case of the threat model 1, function renaming and that co-insertion, okay? We can identify the difference between the baseline and when attacks are carried out. In this case, poison are carried out over the 10% of the training data set, over the 25%, and over 40% of the training data set, just to make the difference. If we take a look, both attacks are affected even with 10% of poisoning. The system is quite affected by that, especially this vulnerability, which has been highlighted, which is directly related to SQL injection. Maybe someone knows what is this. It's just related to databases, attacks in SQL databases, okay? In this case, the attacks can be even bigger, okay? The dangers can be bigger. Now, if we move to the second threat model, meaning that a code which is vulnerable is going to be detected as no vulnerable. If we identify here, well, in most cases, we identify here 100% or almost 100%, meaning that even when just poisoning 10% of the training data set, the attack will be successful. So that's extremely dangerous because maybe you use a public data set which has been poisoned by any of these ways, and well, your system is going to be, well, poisoned in this case, and results wouldn't be the expected ones. But what are the limitations of this work? First of all, it doesn't work for C++. We have make a very deep analysis of a couple of data sets, C++ data sets, but we have identified that codes in which the computational complexity is extremely high, is higher than in PHP or C#, then this approach does not work. Okay, so well, at least is the first step. Obviously, we can apply other ways of processing images because we have applied convolutional neural network, which is the most common way of processing images, but could be others. And also, we have not considered the dynamic code. I mean, in our case, the code is static. I pick up the data sets, just the code, and I processed, but in a static way, not running. Okay, so a module also could be added. So just to conclude, with this system, we are able to detect vulnerabilities. The good point is that we don't have to preprocess the code. And also we have discovered that PHP should be chosen over C#, considering security in both cases, in both threat models. Why? To be honest, we are not completely sure, 100% sure, but we have studied the number of lines of code, of the codes, and also the computational complexity. and we have identified that PHP has a lower number of codes and lines of codes, and also the computational complexity is lower. So because of that, it's probably that the algorithms works better. And if you want to focus on usability, and you are focused on threat model 1, which is the generation of fake alerts, in this case, maybe the sharp is less dangerous. And well, that's all. Thank you very much. And again, thank you all the links organizers.
Thank you for the talk. So quick question, the first one in general. So I mean, what led you to think of using images, right? And are you just taking snapshot of code segments? Does it matter how big the code segments are? And I mean, so in general, right? I mean, how do you structure those images and at what level of accuracy? And the corollary of that question is, are some of the vulnerabilities you're seeing in terms of sensitivity to poisoning tied to the fact that you're actually relying on images? Because I mean, the spacing issue is sort of an obvious sort of situation where, yep, if it's an image, it will think it's different, while if it's a different type of analysis, it wouldn't care, as you were pointing out.
Exactly. Well, thanks. The first point is that using artificial intelligence with images has been used in cybersecurity, but for other topics. For instance, for network traffic analysis, has been used just to discover malware or so on. And I thought, well, maybe for vulnerabilities works. And the good point is that all the preprocessing that other existing works carry out, we don't have to do it. So that's the main advantage. Obviously, there are attacks which in images can be more detected than others. But regardless of the length of the code, the images are scaled. So it doesn't matter. Maybe it does not affect. So we try because we didn't know. Maybe you say, okay, 2 spaces, maybe it's a blank pixel or whatever. But when you see the picture in a big code, it doesn't seem trivial at the very beginning. And if it works, then say, I mean, you know, if it works, maybe it's better than using other techniques, which, for instance, LLMs are used for many things, but LLMs, the resources are incredibly high. So this is why I try to look for other solution, not so resource.